Hello, this is Jose. I will present a data engineering approach for estimating chemical releases from industrial pollution abatement technologies. This is a project in collaboration with the U.S. Environmental Protection Agency, the University of Salamanca in Spain, and the West Virginia University. The agenda for today is first, the motivation to rapidly perform chemical flow analysis at industrial pollution abatement activities. Second, the methodology to use data engineering for gathering useful data and obtaining insights. Third, the case study that is the application of the framework to perform material flow analysis. Fourth, results. And finally, conclusion and future directions. In a previous work, in order to support chemical risk evaluation, we developed data engineering for tracking and identifying the recycling, energy recovery, treatment, and disposal facilities, or AIChEs, that received a chemical waste flow transfer, and also we identified the end-of-life exposure scenarios. Now, we are estimating how much of the chemical flow transfer may be released, for example, as a fugitive air emission at the AIChE by using facility level information. However, improving the chemical flow allocation for chemical releases and worker exposure estimation requires knowledge about the pollution abatement unit technologies, or PAU technologies. Therefore, the objective of this work is to incorporate PAU level information to the chemical flow analysis and improve the chemical flow allocation from facility to process unit level, considering potential internal superstructures and flow streams that may be occurring during the end-of-life operation. Our methodology is based on a generic material balance for a chemical of interest that flows into the PAU technology, thereby allocating the chemical downstream of the operation. For the allocation, we consider the effect of the PAU on the chemical of interest, which is based on the objective of the operation. For example, the objective of a scrubber is to recover a chemical from an input waste stream. Additionally, based on the literature, we identified potential output streams from the PAU technology. For instance, a chemical may end up in a boron or fly ash in an incinerator. Thus, using databases and design configurations like the toxics release inventory, literature about PAU, and environmental regulation, we perform data engineering for transforming the information into a machine-readable structure for future automatization. With this data, we create the PAU dataset, which has features like waste input flow, chemical concentration, etc. Also, we include the unit price of the chemical, or the OPEX and CAPEX, for providing a general and more realistic insight into the type of waste management decision-making criteria. Thus, the features in the PAU dataset enable different applications. First, the information can be used for building data-driven models. For example, we can infer about selecting a PAU technology given the required efficiency and chemical concentration. Second, after the prediction or inference, we can use decision-making tools, for example, to select a PAU technology from the potential candidates that may satisfy the desired conditions. Third, we can perform a material flow analysis. Thus, in our case, we can analyze what happens with a chemical transfer that passes through a AIChE and estimate potential releases and exposure scenarios. Fourth and last application, the release estimates from the material flow analysis and exposure scenarios may support a subsequent exposure assessment. On this slide, we can see a generic procedure that we proposed for development of case studies. First, we used a Bayesian network as a data-driven model. The Bayesian network has random variables associated with the type of waste, for example, whether the waste is liquid waste. Also, we included aspects about waste input flow, the input chemical concentration, the PAU technology, the material efficiency, the CapEx, the OpEx, and chemical price. The idea for using this data-driven model was to infer the probability of selecting a PAU technology under the problem specifications presented on the left side of the slide. Second, we used a fuzzy technique as a multi-criteria decision-making tool for selecting one of those potential PAU technologies. This decision is based on 4 criteria. For instance, we considered whether the same PAU technology could satisfy the pollution abatement requirements for more than one chemical in the same waste stream. Third, the fuzzy inference helps to organize the sequence of PAU technologies. Here, 5 criteria are considered, like the chemical flammability and corrosiveness. Finally, we performed the material flow analysis to estimate the releases, for example, as a fugitive air emission and other output streams. On this slide, there is the information for a case study that uses a waste stream from the celecoxib manufacturing process containing isopropanol and methanol. The table has the problem specifications under which the Bayesian network would infer about the probability of selecting a PAU technology. For example, some of the aspects that in this case we include was the concentration of the chemicals in the waste stream, whether the chemical is a byproduct or impurity, and other interesting aspects. So this slide has the case study results by following the procedure I presented before in the slide 8. First, we can see for this case study that we can identify the PAU technologies that may satisfy the problem specifications and select one to handle the chemical of interest. So, batch steel distillation would handle methanol and liquid injection incinerator isopropanol. Second, we can automatically determine how to construct the sequence of PAU technologies by using fuzzy inference. Thus, batch steel distillation is prior to liquid injection incinerator, as presented the red arrow. Finally, the framework allocates the chemical downstream to each PAU technology, providing the mean value of the flow of the chemical flows in each stream, and also the variability of the results represented by the coefficient of variation. So the conclusion and future direction of this work is: first, the framework can support building a modular approach for data-driven modeling, decision-making, and material flow analysis. Second, the framework can be used to analyze on-site pollution abatement activities. Third, it can be connected to the off-site transfer chemical flow tracking, which was previously developed. We are working on it. Fourth, it can be connected to the circular economy of chemicals. The idea is to track the chemicals, the hazardous chemicals that can flow in a recycled waste flow. We are working on it in this moment. And finally, we need to explore data-driven models for predicting scenarios for chemicals that are not in the data sources. Thank you for the attention. Questions and comments are super welcome.